Now that we've explored Stokes' theorem a little bit, I want to talk about the situations in which we can use it. And we'll see it's a pretty general theorem, but we do have to think about what type of surfaces and what type of boundaries of those surfaces we are actually dealing with. And in the case of Stokes, we need surfaces that are piecewise smooth. Piecewise smooth surfaces. So this surface right over here, it's actually smooth, not just even piecewise smooth. Sounds like a very fancy term, but all the smooth part means is that you have continuous derivatives. And since we're talking about a surface, we're going to think about continuous partial derivatives, regardless of which direction you pick. So this is continuous derivatives. And another way to think about that conceptually is that if you pick a direction on the surface, if you say that we go in that direction, the slope in that direction changes gradually. It doesn't jump around. If you pick this direction right over here, the slope is changing gradually. So we have a continuous derivative. Now you're like, well, what does the piecewise mean? Well, the piecewise actually allows us to use Stokes' theorem with more surfaces. Because if we have a surface that looks like, let's say a surface that looks like this. Let's say it looks like a cup. So this is the opening of the top of the cup. Let's say it has no opening on top, so we can see the back side of the cup. And this is the side of the cup. And then this right over here is the bottom of the cup. And if it was transparent, we could actually see through it. So a surface like this is not entirely smooth because it has edges. There are points right over here. So this edge right over here, if we pick this, let's say we pick this direction to go. And if we go in this direction along the bottom, then right when we get to the edge, then all of a sudden the slope changes dramatically. It jumps. So the slope is not continuous at that edge. The slope jumps, and we start going straight up. And so this entire surface is not smooth. But the piecewise actually gives us an out. This tells us that it's OK as long as we can break the surface up into pieces that are smooth. And so this cup, we can break it up. And we've been doing this when we've been tackling surface integrals. We can break it up into the bottom part, which is a smooth surface. It has a continuous derivative. And the sides. The side, which kind of wraps around, is also a smooth surface. So most things that you will encounter in a traditional calculus course actually do, especially surfaces, do fit piecewise smooth. And the things that don't actually are fairly hard to visualize. And I imagine these ultra pointy, fractally looking things where it's hard to break it up into pieces that are actually smooth. That's for the surface part, but we also have to care about the boundary in order to apply Stokes' theorem. And that's that right over there. The boundary needs to be a simple, which means it doesn't cross itself, a simple, closed, piecewise smooth boundary. So once again, simple and closed, that just means so this is not a simple boundary if it's really crossing itself, if it intersects itself, although you could break it up into two simple boundaries. But something like this is a simple boundary. So that's a simple boundary right over there. It also has to be closed, which really means it just loops in on itself. You just won't have something like that. It actually has to close. It actually has to loop in on itself in order to use Stokes' theorem. And once again, it has to be piecewise smooth. But now we're talking about a path or a line or a curve like this. And piecewise smooth just means that you can break it up into sections where the derivative is continuous. The way I've drawn this one, this one, and this one, the slope is changing gradually. So over there, the slope is like that. Then it's changing gradually as we go around this path. Something that is not smooth, a path that is not smooth might look something like this. Might look something like that. And the places that aren't smooth are at the edges. Not smooth there, not smooth there, not smooth there, not smooth there. But we just have to be simple, closed. So this is simple and closed. And it's not smooth, but it is piecewise smooth. We can break it up into this section of the path, which is that line right over there is smooth. That line right over there is smooth. That line is smooth, and that line is smooth. And we've done that when we've evaluated line integrals. We're broken them up into smooth segments that we can then use to actually compute the line integral. So if you have a boundary or if you have a surface that is piecewise smooth, and its boundary is a simple, closed, piecewise smooth boundary, you're good to go.